London, and he'll tell us about semi-definite programming hierarchies.
Thank you. Yeah, thanks again, the organizers, for having me here and for keep upgrading my talks to more minutes. So I'll try to say as much as I can. Yeah, and so this is I don't think I sent an abstract for this week. Okay? This is semi-definite programming hierarchies for quantum-assisted coding, and it's joint work with Omar and Volker. And yeah, as you will see in my talk, it starts with the same slides as Omar's talk, and then it kind of goes a bit in a complementary direction. And I also talked about this at the CM workshop last year in Vancouver. So whoever already saw the slides, I apologize for that. But I think it nicely fits the workshop. Okay, so let's start. Good. So I think yeah, Omar had a similar picture, or maybe even the same picture on his slide. So what's the setting I want to start with? Okay. So this is all classical. So we have a classical channel between two parties. Let's say Alice and Bob. Okay. So this is just a transition matrix from some input alphabet X to some output alphabet Y, and then we want to send a message of a certain size over this channel. So size K here. And then, of course, we could just put it in the channel and then see what comes out. But if this channel is not identical but noisy, then we should be a little smarter, right? And in particular, we can do an encoder, well, on Ali's side, and then a decoder to again, as good as possible, collect the message again. And here, the setting is really that the channel is given. Okay, I give you some certain channel that is noisy in general, and I tell you how many bits I want to send, and then what we want to optimize is the success probability, so the probability of retrieving the message here on the side, and actually the uniform success probability. Okay, so it's averaged over all messages here, 1 over k. Okay, so I think yes, Omar had this bilinear optimization on his slide. Already, and this is really the fully classical setting. Okay, and now let me again just quickly say I'm interested now really in doing this one repetition of the channel, because especially in channel information theory, people look often at many repetitions of the channel, right? And then they have this coherent encoder and decoders that act on all the systems at the same time. Okay, and then they look at for example, the maximal rate at which you can send bits such that the success probability in this asymptotic limit actually goes to 1. And this is, of course, shown by Shannon. This is given by this nice formula, this nice closed formula, the mutual information of the channel. But yeah, so here we're not interested in this setting, so let me just cross that out, but in this one-shot setting. And now, okay, so what Omar was doing, he was looking at this classical setting, and then he was also looking at a quantum generalization of that, namely when the channel itself was quantum, right? And here, what I would like to look at is we keep the channel classical, but we just add some quantum assistance, okay? So that's why the title, Quantum Assisted Channel Coding. So what does that mean? So we still have the noisy channel here, but now we allow to have any bipartite quantum state here, okay, living on some Hilbert space, or two copies of some Hilbert space here, and we can use this resource, this in general entangled state, to do channel coding, okay, to transmit our message. Now what happens in this case? Well, we still have the message, but now the encoder, well, this will in general be a measurement of m, right? So give it so for each I, this will be a p of m with the alphabet over x that acts on this part of the quantum state, and then puts something classical into the classical channel. And then the same for the decoder here. So for each y that comes out of the channel, this will be again a p of m over the alphabet I now here. Okay. So now, okay, so that's the picture, that's the setting. If you want to like write down what this means mathematically, right? Then you end up with a program like that. Okay, so in the objective function, it's the same as before basically, but okay, so the e's and the d's, these are now measurements, And so, and the phi is this quantum state that you give, okay? And so the objective function is actually replaced with this term. And then here these are just the conditions that the e's and the d's are actually measurements, okay? And of course, as you can see here, so this is again the classical program. I'm not sure how well you can see it. But before, okay, bilinear optimization. So we had the e and the d in the objective function, and we had to optimize overall of these e and d's. And the quantum case, it's very similar. So we really just have in some sense, a non-commutative extension of this classical optimization. So in particular, we have these matrix valued encoders and decoders now, and also we have to optimize over all possible quantum assistance here. Okay, so I'll tell you, okay, you can use anything, any quantum system. So we optimize overall all these possible realizations. Now, in general, this classical success probability, if you want to compute it exactly, well, it's a bilinear optimization, so it's in general NP hard to actually compute this. But now in the quantum case, it becomes even worse because we have this, at least a priori, unbounded optimization here now, right? So, in particular, there is no like dimension upper bound on the Hilbert space H. So that means that in general, we cannot even say if this quantum optimal success probability now is computable. Okay. So I guess the setting makes sense so far. Okay. So now, what is this talk about? Well, the idea is that I want to understand, or we want to understand, what's the difference, right? I mean, this p star, it's never smaller than p, but how large is this gap? How large can this gap become in general? And okay, so you can really think of this as in some sense as a two-player game or a Bell inequality if you want, okay, where we want to understand how much quantum advantage you can get, but really in this information theoretic setting where we look at a fixed channel, okay? So it's like, I think Omar also used this term already, it's like a channel game if you want. Good. Now, first thing to notice is that it's actually known that if we go to this asymptotic IID setting, where we have many repetitions of the channel, it turns out that, at least in first order, asymptotically, okay, remember this the capacity, so that asymptotic rate at which we can send bits over the channel perfectly. So this is not improved. Okay, it's a well-known result in quantum information. And okay, this might be a bit discouraging, right? Because okay, so maybe this question just becomes trivial, and the entanglement assistance, quantum assistance, is actually useless. But again, I'm not interested in this setting, so otherwise, yeah, it wouldn't be that interesting, right? And it turns out that it's actually a non-trivial question, because well, there's an example for which there's a separation between p and p star. So there's nothing particularly insightful about this example, at least from my point of view. It's just this is a transition matrix, okay? I think it has like input size 4, output size 6, okay? So you can look at this channel, and then so for the rest of my talk, I'm actually going to assume that the classical value, okay, this p value might also be hard to compute, but I will assume that we know this p, okay? So we know the p, but we're interested like how large the p star becomes and how large the gap becomes or not, okay? And so for this example, again, we can compute the p, okay? So it's given by 5/6, but then some other people came up with a strategy, with a quantum-assisted strategy that actually beats this p, okay? So we know that p star, so this is for sending 1 bit, okay? You send 1 bit over this channel. The p star is actually is larger, okay? There's some strict gap. And then in some other papers, it was also shown that this gap, sorry, there's a question. Yes, please. Yes, this strategy is simple, yes. Yes, something like this. That is simple? What it is, I don't remember, honestly. Um, yes, okay. But my message will be that if you go to higher dimensional systems, you can actually do better, okay? So, yeah, I apologize. I don't remember exactly how it looks. So, it's reasonably simple. Okay, so the point is it's also optimal, as shown in those papers, if you restrict to these two-dimensional assistants, okay? But again, in general, I didn't want to only allow like 2-qubit, right, two-dimensional assistants, but I wanted to allow unbounded assistants, okay? So that, of course, okay, it's a very specific example, but just to give you the flavor of this type of work. So now we know, okay, this at the p star, it has to be at least the 0.9. Okay, it could be all the way up to 1, but what is it? Okay, right. Okay, good. So now, of course, we can improve the lower bounds by giving better strategies, right? More refined strategies, looking at higher dimensional assistance to doing something constructive in that sense. But what is hard is to get upper bounds on this p star, right? Because in general, there's no dimension bound on the Hilbert space. So how do you derive upper bounds? And so this is what we do in our work. We give hierarchy of STP relaxations that give upper bounds on this value p star. Okay. So in particular, if you look at this STP1, the first level, this will give us an efficiently computable upper bound, and then okay, we can add more and more constraints to get to the higher levels of the hierarchy. And if we actually go to an infinite level, then it also converges back to the p star. But of course, this will be again of infinite size in general, and so it becomes inefficient if you're really going to take the limit. And actually, we cannot say anything on the speed of this convergence. So, please. The commuting. So I didn't really mention that here. Yes. We will talk about that in a second. It is actually related, and basically what happens is we add some more constraints. So the convergence is potentially faster. But and for some examples, you need these constraints to see that at the finite level you already converged. But I'll talk about it in a second. Okay. Yes. Good questions. Excellent. Yeah. So let's look at the idea. I mean, this is again just the p star quantum bilinear program, right, from before. So nothing happened yet. And well, as we already heard now, there are of course lots of ideas out there how one can derive STP hierarchies. In particular, the classical works by Serre and Berta. And I think it's fair to say that in the quantum setting, the authors that kind of pioneered this idea for the non-commutative setting is it's Miguel and his co-authors, and this is called what's called the NPA hierarchy. And I think this came up first in the study of Bell inequalities and how much they can be violated by quantum mechanics. But they also do study general non-commutative polynomial optimization. Okay, so in the sense of this program. Okay, so here we have a bilinear program or a quadratic program, but they study generally non-commutative polynomial optimization. Okay, and I'll comment. I think of the next or one of the later slides on the relation of this NPI hierarchy to our work. But the ideas are very similar. Namely, so now let's look at a feasible solution. Okay, let's look at a triple of a phi and an E and a D. And then every feasible solution defines a gray matrix. Okay, this matrix is going to be a positive semi-definite by definition. Okay, so it's this matrix omega here, and okay, so I drew four different parts here basically, because it's only the upper right part here. Okay, when this index I is equal to the j, that's actually featured here in the objective function. And another thing I did here, okay, there's this inequality here. Okay, so this is actually the exactly the question of Laura. So here we go from a representation which is of tensor product form to just a commuting representation. For practical purposes, I think, yeah, we can treat this the same. I don't want to go in this direction, but in principle, there's a relaxation here happening. Okay. Okay, and now instead of optimizing over all psi's, e's, and d's, we can now just optimize over matrices omega, okay, which are of this bounded size. This gives us relaxations of the original bilinear optimization. Of course, we also have to formulate the constraints on E and D. Okay, so we had these original constraints on E and D. We have to be able to formulate those as positivity conditions on this matrix omega, right? To really get an STP relaxation. Okay, now the point is that one can do that. Okay, so for this first level of the hierarchy, so this gives this upper bound STP1 on P star. we can just write it in the following way. And so you see here, instead of the psi, the E, and the D, we just have a matrix omega, which well, it's a positive semi-definite matrix, which is of this size. Okay, so for every like given channel and number of messages that we want to send, this is a finite size, right? So we optimize over those, and then if you translate the constraints on E and D to positivity constraints on this matrix omega, this is what you get. Okay, I don't want to go into any details about that, but let's just quickly go back to our example from before. Okay, so this example from before, this is just what we had already. Okay, so this is the channel. We want to send 1 bit. The classical value is given by 5/6, but this P star value, we only have lower bound. Okay, and now, okay, so why do I keep talking about this example? Well, this example is very nice because now we can actually show two things. So first of all, of course, we can calculate now this STP1 for this channel and the 1 bit to send, and then it comes out to 0.908. Okay, so and you see this doesn't match necessarily. There's still this gap. So we don't know what P star is exactly, but then one can write down actually a strategy with 4-dimensional assistance, and this actually achieves the 0.908. So that means that the STP1 actually already gives the quantum value. Right? Okay, it's very, very specific example, but nevertheless, you can see the power of these methods. Yes? So I think what we did at first is, well, maybe Omar can also comment more on this, but we kind of thought that, you know, we have to go to higher levels, right? So we're trying to do like STP2 and stuff. And then, actually, I think Omar came up with this. So is Omar here? So I think you can, this is a whole type of class of channels, and you can look at higher dimensional generalization of this. And within this class of channels, I think there is some systematic behavior going on here. But yeah, Laura? No, this is, no, definitely not. No, this is just, yeah, I agree. No, I mean, if you want, it's all coincidence, at least a priori. It's not Omar. But I think there's a whole class of channels for which you can analyze the behavior, but I can't really say much more. I'm sorry. Yeah, thanks for the question. Excellent. Okay. So now, okay, let's go just for this first level. Go to the NPA hierarchy. Now the thing is, that if you apply the NPA hierarchy to this problem, which you can, right, because it covers general polynomial non-commutative optimization, so you're actually missing out on one constraint, namely this matrix is also entry-wise positive, okay, for this STP1. And actually, if you don't put this condition, the value of this program will just be 1, which is, of course, a trivial value, because, you know, it's a success probability, so it can be at most 1. So in particular, the NPA, at least the first level of the hierarchy, will not give you the correct value here. And okay, you can also put these non-signaling bounds that Omar mentioned quickly, and this bound will also be 1, but okay. And yeah, so again, going back to the talk this morning, one thing that Omar presented is that now instead of looking at this STP1, one can actually forget a few conditions here and go to an LP, to a linear program. And then what Omar and Sid could show is that the value of this program is not too far away from the original success probability. Okay, so this, I don't know, it was 1 over 1 minus e or something. I don't remember the exact value, but it's a constant. It's independent of the alphabet size of the channel of everything. It's just a constant, and it's actually a small constant. Okay, so this shows, well, this shows that, and this LP1, sorry, one last, this LP1 is actually the non-signaling value for those who know about this. So this shows that for this type of, let's say, channel games, okay, there cannot be a large separation between the plain success probability and the quantum-assisted success probability. It also shows that if we, you know, if you do this STP1, STP2, all this whole STP hierarchy, I mean, all we can gain by doing is really refine this relation here, right? So we already know that an LP relaxation does well. So if we do this STP1, STP2, and so on, we're always in here. So we're just refining, basically, how much better. Okay, so this is the non-signaling assisted value, and these STPs gives upper bound on entangled value, right? So we're refining between the entanglement assisted case and the non-signaling case. One should also say that this result actually came slightly after our work here. Okay, so we didn't know this to start with. Okay. Good. It was this channel coding and this particular example. But of course, we can ask, okay, maybe we can even do something a bit more general, right? So what's the general form of programs that we can cover? So this is, again, the quantum-assisted channel coding. So again, nothing happened here. But we can now go to general quantum bilinear optimization. And by that, I just mean a program of this form, okay? So now, this E and D, they don't necessarily need to be encoder or decoders, okay? They could just be any non-commutative variables realized on this space H, and here you have this the inner product with the phi vectors, and then the constraints here. So before we just had that E and D had to be a POVM, right? But in general, we can cover any types of affine constraints, okay? So, or a set of affine constraints. Okay, so maybe you think this program doesn't look very general, but it actually treats quite a few problems that we're interested in quantum information. Okay, I think I'll mention that in my conclusions, what problems these actually are. And then maybe one thing that recently one commented on, so we call this bilinear optimization. Well, it's linear in the variable E, linear in the variable D, but it's important here that we also optimize over these psi's, right? So you might also call it trilinear, but this is really the setting that we can cover. So for example, in the second part of Omar's talk this morning, he was looking at quantum channel coding, right? And in this quantum channel code, the psi vector was actually fixed. Okay, so it was fixed on the Hilbert space was fixed, and this psi vector was also fixed. But here the setting is really that we want to optimize over those as well. Okay. Good. And then if you now write down this STP1 for this general setting, the STP you get is of this form, and okay, again, might be not very insightful. So let's again compare it though to the NPA hierarchy. So I hope there's no mistake here, but I try to write the NPA hierarchy in the same notation that we're using. So this is some potentially different first level STP tilde. And okay, now you can look at these two programs. They look very similar. However, as you can see, now one more spec. No, there was actually, we can go back quickly. Maybe there was a question I wasn't able to answer. So the question was, maybe you can ask it again. Actually. Great. Thanks, Omar. Also, thanks a lot. Perfect. So I think I was talking about the general setting now of quantum bilinear optimization and how our first level compares to the first level previous work of the NPI hierarchy. And you can see here we have more constraints here in this condition, because if you put one F here as the trivial constraint, okay, and then you get back these constraints, but of course you have these mixed constraints where you have two different F. However, again, here we have to be a bit careful, because actually the way we relax things, STP is going to be much larger. So the first level is not going to be the same size as the first level of the NPI hierarchy. So actually, to be fair, one should compare all the levels in some sense. Okay, so the question is if then these type of constraints, if they show up in the NPI hierarchy, but just at the higher level, because even at this higher level, the program might be of the same size as our STP on the first level. And it turns out that some of them indeed show up. So whenever you have some mixed constraints, so remember we had these two type of constraints, okay, one from the set G, one from the set K. So these mixed constraints, they actually show up in the higher levels of the NPI hierarchy, but there are some that never show up, okay? Now, of course, we know the NPA hierarchy actually converges. So in that sense, those constraints are not needed if you want. However, they can help you a lot in practice, at least potentially, right? So for example, this channel I had on my slide before, these constraints were actually saving us. These were the constraints that gave us on the first level already a non-trivial bound, or the actual P star value. Okay. Good, yeah. So I didn't really talk about how to get the higher levels, but okay. So the idea is to consider higher order products of the variables xu. Okay, so the variable xu is just given by the encoder E and the decoder D. So for example, if you look at the second level, okay, so you will optimize over a larger matrix, let's say omega 2. That is constructed in this way. And also you can check that it's going to be a positive semi-definite, and so on and so on. But of course, if you go up in the levels, it becomes, size of the program becomes large, and it becomes quite messy. But we can prove that our hierarchy actually converges to the p star value. Again, in principle, this already follows from the convergence proof of the NPA hierarchy, because we just add more constraints to the NPA hierarchy if you want. So we also give an independent proof, but in principle, you could actually deduce it from the NPA work. Okay, good. Yeah, so again, I guess the main message here is that these additional constraints, they can be important for applications, and well, sometimes analytically, sometimes numerically, but they can become useful. Good. Yeah, so that already brings me to the conclusion slide. So what did we do? Well, we derived this improved STP outer hierarchy for bounding the quantum advantage. When you look at bilinear optimization versus quantum bilinear optimization, and in particular, it's also how I started. We looked at this quantum-assisted channel coding, right? Here, I just want to mention that this bilinear optimization form actually fits many other problems. Okay, so for example, well, it fits this well-known setting of two-prover games, and here, yeah, it just adds new conditions, right? Again, to the compared to when you just apply the NPA hierarchy, and yeah, so these guys in 2016 they also independently derived the first level relaxation in their work, and okay, but we can look at more problems even. So one problem we have been interested in for a long time and is still pretty much unsolved is you can look into cryptography, okay, and then you can ask how much more powerful quantum adversaries are compared to classical adversaries. And so in particular, if you have some classical cryptographic protocol, you can attack it with a kind of a quantum memory attack, and you can ask, you know, is the protocol still secure if the adversary has this quantum memory attack? And in general, the gap there, the gap between the power of classical and quantum adversaries is very understood very poorly only. And okay, so we can give upper bounds on the gap, but analytically we can't show very much. So this is really kind of an open problem. And then finally, these methods, you can also use them to give an outer hierarchy for optimization over the completely positive semi-definite cone. And these type of optimizations actually cover many quantities we're interested in quantum information, including quantum graph parameters, zero error quantum information theory, so problems from that field. Okay. Yes. Now this is all very nice, but again, I want to refer back to Omar's talk this morning. Namely, so what we did here, we started with a classical problem, basically, right? And then we added entanglement assistance, or okay. So here in the cryptography setting, it was like not assistance, but yeah, it was kind of evil assistance. We gave assistance to the adversary. But instead of doing that, of course, you can make the problem itself quantum, right? And it was Omar talked about this in the second part of his talk this morning, and I think so. He did this for channel coding, but I think even for these other type of problems, you can also look at fully quantum generalizations. I think this should be interesting. Okay, thanks a lot. That's all I had to say.
Any more questions?